Hello again. In this video, I will talk about the air mass and what it means if we are considering solar cells. So the air mass is a bit confusing maybe, because you might think, so what does it matter what the mass of air is if you're operating a solar cell? And I guess the term has some reasons from history, but here we're going to look at what is meant by this. So if we are considering the sun out in space and we're considering our Earth here, and here I'm just showing part of the Earth's surface, we have the atmosphere above the Earth's surface. The atmosphere has different humidity, different ions in it, and therefore it absorbs sunlight and it also might scatter sunlight. So the atmosphere has an influence of what part of the sun radiation is actually reaching the Earth. And that is the important point that is discussed with the air mass. So it's not about the mass, but it's actually about what fraction of the sunlight that the sun emits actually reaches the surface of the Earth here. And the first important point to consider is that it, of course, depends on the thickness of the atmosphere and on the different constituents of the atmosphere. So how much water, which temperature, what particles, is there dust in there, are there different ions in there, how clouds, of course, will also influence it, but let's assume we don't have clouds for now. So that means the atmosphere has a big influence on what radiation reaches the Earth. And one point that needs to be considered then is, first of all, that it depends on where you are on Earth. And here I've drawn two different scenarios. So if you are right here where the sun is up at 90 degrees in the zenith, then you would have what is called the air mass 1, because you have the shortest distance through the atmosphere. And this shortest distance through the atmosphere is then what you at least have on Earth, and that is defined as the air mass 1. So going once the shortest distance through the atmosphere. And this air mass 1 is then considered, of course, it still depends on what are the weather conditions and so on. So there are spectra defined that are taken as reference spectra for certain conditions of the atmosphere. So for given conditions of the atmosphere, the air mass 1 refers to going at a 90-degree angle, so straight down to the Earth. And of course, this never happens in Kiel here because we are too far north. The sun will never be at 90 degrees. So we will always have a longer path through the atmosphere, as shown here, if the sun is shining down on Kiel here. So we definitely always have a longer path, and this is seen also in this radiation here for the sun rays coming to Kiel city here. And then, of course, it depends on the time of the year. So it's not that Kiel always has the same air mass, but because it doesn't have always the same sun position. But it depends on, are you early in the morning, the sun is just rising? Is it later in the day, the sun is higher up? And then later, then towards evening, the sun is going down again. So also, it very much depends on the time of the day, what the position of the sun is and what the air mass is. And it depends on the time of the year. So in summer, the sun is higher up, while in winter, the sun is not rising up so much. So even if you average over one day, it will be different for the different days of the year. And to describe now what is the condition of a certain location, this air mass value is used. And this air mass value is then defined as the length at the position where you are at divided through this shortest length if the sun is right at the zenith. And you can actually calculate this by just using the cosine here. So the length through the atmosphere at an angle of 41.8 degrees, for example. so this would be this position here, is given then by, the air mass is given by 1 over the cosine here, because basically if this is length L zenith, then this length here is given by L divided by the cosine. So it's longer than the one at air mass 1. And actually this 41.8 value, 0.8 degree value here is chosen because if you plug that into the cosine, then you obtain 1.5. So an air mass of 1.5 corresponds to 41.8 degrees of the sun as seen from the horizon. If you measure it from the zenith, then it corresponds to 48.2 degrees. I mean, you need to plug the 48.2 degrees into the cosine to get the correct air mass of 1.5. Okay, so depending on which time of day you have, you have a different air mass value. One more thing to consider is that the Earth is not flat, but it's round. So actually, you might think from this image here is that if it's getting later and later in the day and the sun is going down more and more, the air mass might approach infinity. This is actually not the case, and if you think of the Earth as being round, you can actually see this here, that if the sun is going down here at this location, that is the beta angle is 90 degrees, you still go through a finite amount of atmosphere because the atmosphere is surrounding in a spherical shape the Earth. And so the approximate value for the air mass at 90 degrees angle or at sunset or sunrise is 38. So that is again 38 times longer than the path than what I showed here. And so you can see my schematic is not very good because it's not 38 times longer here, the path, but much less. So from that we know the atmosphere has to be significantly thicker than what I drew here in order to obtain this value of 38 times more path length if the sun is setting compared to we have the sun right up at the zenith. Okay, so on Earth, we have on the surface of the Earth at sea level, we have air masses from air mass 1 as the minimum value for the air mass to higher air masses up to something about 38. If we are out in space, then of course the sun does not have to pass through the atmosphere, and therefore the air mass in space is 0. So air mass 0 means we are in space, and that is the full radiation we see in space without the absorption by our atmosphere. Then you might ask, can the air mass also be somewhere between 0 and 1, or is it always between 1 and 38 or 0? And yes, it can also be in between if you are thinking of situations where you are higher up in the atmosphere. Let's say you are in a plane, for example, then you would be at a higher altitude, and therefore you have less absorption by the atmosphere than this air mass 1. And therefore, you can also have an air mass value of 0.5, for example. So the air mass values can change between 0, which is out of space for us, to something like 38 or something where you describe the longest distance through the atmosphere. Okay, so one more point about this air mass. So if you are working on solar cells, you will see a lot of information, or in all the papers it will be published with these solar cells were tested at air mass 1.5 or air mass some value under certain conditions. And now you might wonder, I mean, why don't you just take the solar cells outside, like we have solar cells on our roof, and just test them in the real conditions, which of course is what you really will have afterwards. And that you don't do, because then you wouldn't have any comparability. So actually, in order to test solar cells, you create in the laboratory well-defined conditions that exactly reflect the air mass 1.5, for example, in order to have comparability between the different solar cell modules. On the other hand, it means if the solar cell that you bought, like if you have a solar cell here and it has a certain amount of energy that it delivers under AM 1.5 conditions, and maybe your sky, you are at a different location, your sun is lower already because it's not high noon, your sky has a different turbidity on that day, or there's dust or something, then that of course means you don't get air mass 1.5, and your solar cell will not exactly perform as it is classified for at air mass 1.5. So the classification is for the laboratory conditions to get the comparability, but the actual measurements, of course, then out in nature depend on what the local conditions of the atmosphere are, how much energy reaches the Earth. Thanks for watching.